4.6 talks about modeling with exponential functions. So they have n equal n sub 0 e to the rt. We know about a equal p e to the rt. I'm going to use this instead. All what you have to do when they say in the book, find a formula, they're not going to write a, they're going to write n instead. And instead of p, they're going to write n sub 0, which is the initial amount, the same r, the same t. So here, p is the initial amount, r is the rate in decimal, t is the time, not in years anymore. It depends on the problem. Some problems it will be years, some problems it will be month. N is the amount left after a given time, which is our a. So I'm going to stick with this. So here we start. A certain species of fish was introduced into a lake 10 years ago. So the population doubles every 7 years. And now the population is 9,000. What was the initial population size? Now you're going to figure this out quickly. I need to figure out the initial population and the rate of increase or decay for every problem. If it's given, I'll use it. If not, I have to find that. So this says a certain species of fish was introduced into the lake 10 years ago. The population doubles every 7 years. And now the population is 9,000. So what was the initial fish population? I'm going to say the fish population is the initial amount, and that's what I'm looking for in this problem. E to the RT. Well, this is what I know. It was introduced 10 years ago. So that's at t equals 0. Now, when t equals 10, the population is 9,000, right? And it doubles every 7 years. So if I start with, well, all right, let's say the initial amount was 10. When it says it doubles every 7 years, in 7-year time, right, that's going to become 20. If the initial amount was 50, in 7 years, that's going to become 100. If the initial amount was p sub 0, in 10 years, it's going to be 2 times that. Now, if you don't like that, that's okay. You could use 100. Anytime they don't give you the initial population, you could say, let's say the initial population was 100, for example. But in 7-year time, it's going to double. In 7-year time, that initial population will become 200. And if I fill in the blanks, 200 equals 100 e to the r times 7. This allows me to find r. So in this case, simplify or isolate the exponential by itself, divide by 100 both sides, and I'll get 2 to equal e to the r times 7. Transform to log form, and I could say r equal natural log of 2 divided by 7. Now I could write it as a decimal, I could leave it like that. If I write it as a decimal, I need to carry enough decimal places. That is, if I take natural log of 2, divide that by 7, you'll notice it's a big decimal, 0.0990 210. So at least 5 or 6 decimal places. Now this is what I know. Now I know that a equals p times e. So either you write this as r or you write this as r. I'm going to go one time with the decimal. And what do we know? We know in 10-year time, e to the 0.0990210, we know in 10 years time, whatever the initial population is, it just became 9,000. And now I can solve for p, dividing both sides by this exponential, and I'll get the initial population to be 9,000 divided by e to the 0.0990210 times 10. I'm going to show you the use of this answer key. You notice this is the last calculation I made. That in my calculator is stored in the answer key, and the answer key is right there. The last calculation that you do is always stored in the answer. So if I do answer enter, that's what's stored in there. So no need to rewrite it. When I want to come in and figure out what this answer is, I'm going to plug it in the calculator. I'm going to take 9,000 divided by parentheses, the exponential, raised to the answer, instead of me writing all of that number, times 10. The calculator tracks the last thing that we did. That's always the case. And that's the nice thing about a scientific calculator. 3,343.48, but we're talking about people, right? Population. So we're going to say it's 3,343. 3,343. So we always round to the nearest person. If it's money, to the nearest dollars, pennies, and if it's bacteria, people, fish. So now I know the amount present at any given time is 3,343 people, e to the 0.0990210 t. That goal is always to find the initial population and the rate of increase or decrease. Now I could answer any questions they have. They say, estimate the fish population in 12 years. Well, A will be 3343 e to the 0.0990210 times 12. And the population will be, now that's what's stored in my calculator is that number. If I go back to the previous, what I wrote, there it is. And I could check, that's stored in my answer. Now if I take 3343 times e, some calculators you don't have to write the times, it figures that out automatically. If I put answer, there it is, times 12, and it's going to be 10,969. Since that's a 5, I'm going to round up. 10,970. 10,970 fish. Sketch a graph. Well, can you graph this? Yeah, that's exponential growth. Now we're going to get a rough sketch. Of course, we don't want an exact graph. So this is exponential growth. It looks like this. Of course, you don't worry about the negative. You start with 3343 and it's growing as time passes by. And this is in the book, they'll write that as n. Same thing. Alright, so first problem is always the worst. The rest, you'll see we're doing the same thing. A certain species of fish has a relative growth rate. So they gave me R. That's going to save me a lot of work per year. The bird population was 30,000. They told me the initial population. They gave me everything. That's at t equals 0 indicate it's the year 2015. Right? So A equal 30,000 e to the 0.0135 t. Got it. Nothing to do. In the previous problem, I had to find all of those. Here it's given. Estimate the fish population in 2021. Well, it's kind of like your birthday. If you were born in the year 2015, by the year 2021, 6 years have lapsed. So A will equal 30,000 e to the 0.0135 times 6 years, and that will tell you what is the population right now. And let's see how that works. 30, 1, 2, 3. Again, this calculator doesn't need times. Your calculator maybe needs it. Make sure you check as you're doing the homework before you get to the test. Times 6, enter. 32,531. 32,531 birds will be present 6 years from now. And of course, how long until the bird population reach 60,000? how long you're looking for time until A becomes 60,000. Basically, they're looking for the doubling time. That's extremely important in applications. Replace A, again, the equation is right there. Replace this by 60, 30,000, 0.0135t, and you're going to be doing the same thing for every problem. Isolate the trig function by itself, divide by 30,000, and you'll notice that's going to be 2 equal e to the 0.0135t. Transform to exponential form, to log form, divide by 0.0135, and t will equal, in this case t is in years. Get your calculator out and take natural log of 2 divided by 0.0135. It's going to take 51.34 years. 51.34 years for that to happen. Sketch a graph. Again, there's the graph. The graph is supposed to pass through all of these graphs look the same. Of course, you ignore that. This is 30,000. This is time in years, and this is the population, N or A, whatever you want. Here's another problem. A frog population was 20,000 in 2003. Well, let's say year 2003 is the year somebody was born. So let's say right now, A equal 20,000 e to the r times t. Okay, we get the initial population, and we assume starting from now. The population tripled in 12 years. What does that mean? Whatever you had 60,000, it tripled. It became 60,000 in 12-year time. Well, can I solve for r? Divide by 20,000 both sides. And you'll notice I'll get 3 equal e to the 12r. Transform this to log form, or log both sides with base e. And r will be natural log of 3 divided by 12. So again, you could write it in decimal, you could leave it as is, but since I'm going to store that in my calculator, it doesn't matter. Natural log of 3 divided, natural log of 3 divided by 12, there it is, 0.0915, 0.09155, 102. Again, so now my equation reads A equal, or N equal, that's what they like, 20,000 was the initial population, assuming we're starting at 2003. E to the 0.09155,102t. That is the formula. What I need to find, I already listed. The question is, how long does it take for the population to reach 200,000? How long you're looking for time until A is 200,000? Well, there's the equation. Replace A by 200,000. Isolate the trig function by itself. We just did that in the previous section. And 3 zeros cancel out. 0 cancel out. 2 divides 20 10 times. So we're looking for how long does it take for the population to be 10 times as much. Log both sides or transform this to log form. Remember, this ugly number is stored in my calculator as an answer. I don't have to input that. Not that it's too hard to input that. It's just that there's no point. Since you're using technology, use it right. So I already have stored in my calculator that number. So I take natural log of 10 divided by my answer. And there it is, 25.15 years. 25.151 years. Let's go 3 decimals, and there it is. Okay, let me get the next problem as well. It says, the count of a culture of bacteria was 100. The count of a culture of bacteria was 100. So at t equals 0, it was 100. So I know that that's P. After an hour, oh, I'm sorry, forgive me. The count of a culture of bacteria was 100 after 1 hour. So when t was 1, A was 100. And when t became 8 hours, A became 300,000. What is the relative rate of growth and the initial size of the bacteria? Well, let's see how this works. If I take A equal E to the R times 1 times P, and here, if I say 300,000 equals P times E to the R times 8. Now look at the top equation. Can't I say P equals 100 over E to the R? Now take this and substitute it right there. Wouldn't that mean 300,000 equals the 100 over E to the R times E to the R? Well, don't you subtract those when you divide? Isn't that saying 300,000 equals 100 E to the 7R? If I isolate the trig function by itself, divide by 100 both sides, I'll get 3,000 equals E to the 7R. Natural log of 3,000 equals 7R. So R is natural log of 3,000 divided by 7. Natural log of 3,000 divided by 7. 1.143, 1.143, 7668. 7668. Okay, now what? Now, if I take R and I plug it in there, shouldn't I get P? So the deal now is if I take this and say 100 equals P times E, and instead of R, or actually it's right there, can't I say P equal 100 over E to the R? And E to the R is 1.1437668. So the initial population will be how many? And if I was to go ahead, remember, I already have that number stored in my answer. If I take 100 divided by E to the answer, I'll get 31.86. I'm going to say 32. So my formula is A equal 32 E to the 1.1437668 T. This population is growing very fast. If I look at, find the model, apologies. There's the model. So I get R right there. And then it says, find the number of bacteria in 5 hours. Oh, I see, that didn't move. I made a mistake. Okay, I see. And did it run into the other one? Almost. Oh, crap. Okay. I should have shifted the whole thing. I didn't shift the whole thing. My mistake. Okay. It says, find the bacteria population after 5 hours. A equal 32 E to the 1.1437668 times 5. And that's what it is. No big deal. If I go back twice, oh boy, okay, never mind. I'm going to take 32e raised to the 1.1437668 times 5. That population will be 9,746. Right? Remember, it took it 8 hours to reach 300,000. And how long will it take until the culture reach 100,000? 100,000 equals the initial 32 e to the 1.1437668 times 5. Isolate the trig function by itself, the exponential by itself. You could reduce that, you could leave it as is. And now take natural log of both sides. Since I have the technology, no need to spend time on simplifying. So t will equal natural log of 100,000 divided by 32 all over 1.1437668. And t will be how many hours? And if I plug this in my calculator, I'll take natural log of 100,000 divided by 32 over 1.1437668, 7.1 hours. 7.07 hours, let's say 0.73 hours. So notice, in 8 hours it reached 300,000. To reach 100,000 it has to be less than 8 hours.